Well, there are three purposes of this talk. The first one is, as Matthias advertised yesterday, I'd like to give a complementary viewpoint on Moonshine, which is from the modular form point of view. And secondly, I would like to give an overview of the developments that go beyond mature Moonshine in the past few years, and then well, it would be mostly reviewing the talks I'm personally involved with. And especially Suresh is going to talk about M12, so I'm not going to cover that. And Hikami-san is going to talk about the n=2 Moonshine, I think, so I'm not going to cover too much of that. And then the third purpose is, along the way, I wish to cover some dry stuff, like, you know, the definition of mock modular forms and, you know, a bit of more definitions of Jacobi form, because we also have many mock modular form and number theorist experts here, and I wish everybody could make some use of that. So without further ado, let me just start. And well, I'll start with a summary. So if you have only like 5 minutes attention span allotted to this talk, it's the time to use that 5 minutes. So summary. So on this part, I'm just going to summarize what I call the Umbral Moonshine, which is sort of a framework that generalizes, or no, extend, I mean, the the mature Moonshine. So the picture is the following. We start with a lattice, a Niemeyer lattice called Lx, and which is labeled by x, which is its root sublattice. I'll define these things in a bit, but now just pictures. And what you can do from this structure is you can define a finite group that's I call the g of x, and you can define a cusp form of weight 3/2. So I'll define these things later if you don't know. And via this cusp form, one can uniquely construct a vector valued mock modular form with 2m components with certain properties. And right, m is an integer which will be given by the data here, or I'll tell you now, m will be the Cossiter number of the root system. Okay.
You're not restricting to Umbral Moonshine, you're doing Niemeyer Moonshine.
Umbral Moonshine is Niemeyer. No, I mean, what are
So I mean, you're not restricting to just A copies of A's, right?
No, yeah. We're not just doing pure A type. Yeah, sorry. And then this, in the later part of my talk, I will tell you more about this definition and this construction. And what I won't tell you is how to generalize it. There's a way to generalize it for every conjugacy class of this group that you defined here. And so you generalize like this construction to get to another set of mock modular forms for each conjugacy class of the group you define here. With this data, then Umbral Moonshine has the following content. So it says that take your favorite Niemeyer lattice. There are 23 of them. I'll define it later why it's 23. Take your favorite Niemeyer lattice, and this conjecture say that there exists a module or a representation, if you want, of this finite group that I defined there. And this module has two gradings, one by R one by a set of integers satisfying this positivity condition. And this module has the property that its graded characters in graded characters. So why am I saying graded character? Because I'm doing this. And here the Fourier coefficient, it's going to be, sorry. The character. And there's a decoration polar term that appears for certain choices of R, namely R squared equals 1 mod for M. Okay, so this is the Umbral Moonshine conjecture. And of course, to phrase this conjecture, you're assuming that all these are already defined. This is well defined, this is well defined.
Sorry. The conjecture is such that this, you said, is a vector of modular.
Yes, yes.
Yep.
Okay. So to put it into some kind of perspective, I'll draw this diagram. So there are 23 Niemeyer lattices, and 8 of them are special. We'll call them pure A, because X has only A-type component, okay? And this is the, for instance, I think this will be related to what Hikami-san will mention later. And especially, well, I need another color. Especially the simplest case is when X is just 24 copies of A1. This is the Niemeyer lattice, for instance, that Kondo have used. Then the group is going to be in M24, and Umbral Moonshine conjecture is the theorem that Terry has proven. So this is the summary. And in the rest of the talk, I'm just going to define these things for you so that the conjecture makes sense. Is there any question? Okay. So let's start with the first part. To spare you some boredom of looking at me writing here, so I've written this theorem here, so I don't have to write it. So the first thing I'm going to define for you is what Niemeyer lattices are, and from there, how to define a finite group. So the theorem of Niemeyer says that there are 24 even, self-dual, positive definite, 24-dimensional lattices. So these 24 has nothing to do with that 24. Probably not. Although, who knows? Yeah. So the first one is a Leech lattice that, for instance, Dave has mentioned yesterday. It has no roots. So by roots, I mean lattice vectors that have norm square 2. And there are other 23 ones, which I called LX, and which for this purpose of the talk will be called Niemeyer lattices. Sometimes we refer to Niemeyer lattices as the whole 24 of them, but since Leech has its own name, so let's just, for the purpose of this talk, call the 23 on the Niemeyer lattices. Okay, so there are 23 of them with some non-trivial root system I called X. So root system, again, is defined in this way. And furthermore, the root system uniquely specifies the Niemeyer lattice. There's for each given of them, there's only one lattice. And these X, 23X, are exactly those 23 root systems that satisfy these two conditions. First, it's a union of ADE root systems, and satisfying the condition that each component, each indecomposable component has to have the same Cossiter number, which are called mx. And this condition is going to show up again and again, so I just call this condition 1.1. And the second condition is quite obvious, that the total rank cannot exceed 24. In fact, the total rank has to be 24 in this case. And well, it's a 3-minute exercise to write down the 23 combinations of ADE diagrams in satisfying these two conditions, and they are the root systems of the 23 Niemeyer lattices. And okay, that is fine, but it's a tiny little bit abstract. But in fact, they show up in very natural context. For instance, well, there's a famous problem of sphere packing, optimal sphere packing. If you want to, for instance, you want to pack your whatever, your macaron in this way, for instance. This is pretty optimal in 2 dimensions. And in 3 dimensions, that's packing your oranges. And if you want to ask for a sphere packing of 24-dimensional spheres, and furthermore, you want a lattice packing, then it's proven by Leach that it's given by the Leach lattice. And in the sphere packing, there are furthermore some interesting points called the dipoles. For instance, these are the points that have maximal distance to any of the balls. And there, in the Leach lattice packing, there are 23 orbits of dipoles, and they correspond to 23 Niemeyer lattices. And another nice construction was mentioned yesterday by Dave. If you just start with the unique 26-dimensional hyperbolic lattice, and you look at its orbits of null vectors, primitive null vectors. There are 24 of them, and for each of them, you can consider, as Dave said yesterday, consider this quotient, and they correspond to the Leach lattice and the Niemeyer lattices. Okay, and the Leach lattice vector is singled out in this language because the null vector here corresponds to coincides with the Weil vector of the Weil group of this lattice. So this is the beautiful 70 thing. Okay, so now I have defined for you Lx. And I might as well just define for you the Gx, since it's easy. The definition is very simple. If you have a lattice, what can you study group theory-wise? Well, it's automorphism group, of course. And then there's a trivial part. Well, by trivial, I don't mean technically, I mean the less interesting part, which is generated by the Weil reflection with respect to roots. You can easily convince yourself that it's part of it. It's furthermore a normal subgroup of it. So you might as well just ignore that part, and the resulting part, you call it G of x. And that is the definition of the finite group that is here. So just to give you some example, again, let's take the simplest x that satisfies these two conditions, 24 copies of A1, then G of x is M24. And of course, it's also the automorphism of the extended binary code and so on. And in this code language, you can also understand it from the Niemeyer lattice language, but I'm not going to talk about it. But it's very interesting. And the next simplest one is 12 copies of A2. And the group is a central extension of the smaller material group N12, and which is also the stabilizer of another Galois code. And let's take a different example involving the D-type. And this group is going to be slightly less interesting now. but so on and so forth. You can define all the g of x in this way. Okay, so that finishes that part. So now we're going to do the modular stuff, if there's no other question. Okay, so now let's do the modular stuff. And as I said, I'm going to go through some dry definitions. And it's like dry but not dry enough. Okay, so here is, as I promised, modular stuff. So let's go through some definitions. It's simple enough. I mean, it's so basic that nobody bothered to write it down earlier. But okay, let's just write it down. And so let's, for the sake of simplicity, we take a subgroup of SO2Z, and we take gamma to be its an element of it, and psi to be a multiplier of it, and then we define an action on the holomorphic function in this way. Okay, this is just a definition, right? So it's a natural definition if you want. And we say that this holomorphic function on the upper half plane is a modular form of weight W. W shows up here, and multiplier psi. Psi shows up here for the group gamma if this action gives back to the original function for all elements of gamma. And I say I'm not even being dry enough because I'm being sloppy in terms of growth. I mean, so I say it's unrestricted because, okay, to be an honest modular form, you also have to, satisfy some growth condition. Especially, there's one type of modular form that's interesting for us, the cusp form, which has a further restriction that f vanishes at all cusps of gamma. Okay. So, huh? Right, yeah.
But you want, it won't be a character, it'll be a projective character.
It will be a projective character. You should go, yeah, that's right. You should go to the metapletic cover in order to, but, yeah. Well.
What's W? Is it an integer?
Yeah, half integer.
Yeah, half integer. That's why. Yeah, because here we do need half integer stuff. Okay, so how about the Mach modular form? Ken has implicitly defined it, but I'll just write it down. I'll add the data here. So this is a cusp form of the dual weight. Dual weight means here on the group gamma. A dual weight means that the weight sums up to 2. And then I twist this action by this function g by adding this term, which is manifestly non-holomorphic. Okay, and this number just depends on W. It's not important. And we say that this holomorphic function is an unrestricted Mach modular form of blah, 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 and with shadow G if this is true. This is invariant. It is invariant under the twisted action. Okay, so that's the definition. So at least we all know what we're talking about here. Yeah.
Just to be a little picky there, don't you need some adjective in front of G modules, like non-trivial? Because otherwise, can't you just have
right, but
everything is just sum of ones?
No, but because I have given you this is specified.
It's already given.
It also
Yeah.
satisfies another kind.
If I take the logic that I have already constructed this, then a module that satisfies this, I think, is by definition interesting.
I see, because the trivial one can't.
The trivial one just have all of them being the same. Yeah.
Actually, can I ask a question? I'm interested in the transformation laws for these examples.
Yeah.
In terms of the Weil representation, do these all correspond to congruent subgroups, say gamma 0 n with genus 0? No. They don't.
You mean this the level of this?
Theta function, you're doing gamma 0, 6. That must be one of them when m is 6 or something like that. There's some
When m is 6. Oh, that's a great question. Indeed, yes. The answer is yes.
But some of them have bigger genus.
Yeah.
No. I think you're asking. So
I'm going somewhere with this.
I think there's two dimensions, right? There's Niemeyer lattice, and there's different congruent subgroups, right? And Terry, I think, is referring to this. The question here being, this guy is under what group? And I think my answer to your question, because you're talking about the m's, the Cossiner numbers.
Yes.
So indeed, there is a very striking genus zero property here.
For example.
Okay, so.
I'm sorry to interrupt.
No. I mean, I really want to talk about this, but I thought nobody might care enough, so.
The reason I'm bringing this up is, as everyone knows, the denominator formula corresponding for J is a way of writing the Hecke algebra in disguise. The Hecke algebra lives upstairs. But the Hecke algebra acting on the J function, or J minus 74, Tm applied to that gives you a canonical polynomial of degree m and j, which is generically irreducible, has lots of beautiful properties. Once you have this set up, now that this Umbral Moonshine is proven, it means that you can use these degrees and generalized things to build Borchardt products for every discriminant delta. If you have a Haupt module, then it's a polynomial in something like J. And people like Larry know how to show that's going to be irreducible generically. And then earlier when we said that for D equals 5, 13, or whatever, those are odds, it means for every analog of Hecke operator, for every one of those discriminants, you have the sequence where the second coefficients are always odd. They'll be irreducible, and they'll be Galois traces, and you can ask, what is the analog of the fields that are generated in the splitting fields of Hecke? So I view there's an arrow that goes down there that branches to number theory where you've already made some conjectures about these Galois traces.
Right.
So if the genus is 0, then it's almost automatic that we have a procedure to do that.
And I think we should talk.
Okay, I'm very excited about that.
Yes.
Because this is the analog of what Zagier wrote down when he reproved in his way the denominator formula. But instead of the Hecke algebra, we're replacing this by generalized Borchardt products. One for every discriminant, not one for every form, one for every every vector value form and every discriminant.
I see.
There's a plethora of irreducible polynomials below that. Sorry.
No problem. So just to explain maybe a little bit the genus zero property that I didn't plan on explaining. Well, there's various ways to explain that, but let's give you the Haupt module. Okay. So for this data x, you can write down something. So we know there's something called the Cossiner exponent, which is the eigenvalue, which is in goes from 0 to 2n minus 1 if you want, which is the eigenvalue of the Cossiner elements. And so you can write something like this. Well, I might get this wrong. So alpha of r is the multiplicity of this Cossiner exponent showing up. Okay, and this q is basically q to the rank over 24, but because we know the total rank has to be 24, so this becomes 1. Okay, so this gives us an infinite product, and it is always a Haupt module of the group gamma 0 m x, maybe plus some stuff that we have control over.
So what is alpha?
Alpha is the multiplicity of this, because for some d types, the same r, the same Cassirer exponent shows up twice. Then you have to correct it.
Sorry, why did you say it's an infinite problem?
Okay. No, it's not an infinite. No. Okay. I'm sorry. I'm screwing this up. So it's like k larger than 0 and k equals r mod 2m. I'm sorry. Yeah.
So this is the fixing group of this gamma naught is the fixing group of the g equals 0 part for that.
Right. And or you might want to, for some people it might be simpler to say that this is, some people are familiar with the translation from cycle shape or frame shape into eta quotient. And this corresponds to the cycle shape of the Cassirer element. Okay, this is basically the same statement, but just translated in different ways.
The G's identity term, sorry to interrupt.
Yeah.
That's going to generally come with a character, right?
Right. So this property doesn't have a direct relation with this guy, but it has a direct relation with this guy if you want. Yeah. But I'll be very happy to discuss this in private. And where was I?
Define Mach modular form.
Defining Mach modular forms. Yes. Right. After defining Mach modular forms, I also want to define Jacobi forms. But fortunately, Matthias have basically defined it already. So again, I'll be sloppy with the growth condition, and I call everything unrestricted. So as Matthias has told us, a Jacobi form, let's call it phi, with weight w and index m, well, is invariant under the modular transformation, which Matthias wrote down, and the elliptic one. Elliptic means you are just transporting a point on the torus along, A and B cycles of the torus, if you want. And this elliptic property leads immediately to a property of the Jacobi form. Okay, I have to say the Jacobi form has to be holomorphic here. That you can write a Jacobi form and decompose it into some combination like this. So R again will run from 0 to 2n minus 1. So the slogan here is, if you want, Jacobi form contains the same information as a vector-valued modular form. So this is the H, and this is the phi, right? And it's a vector-value modular form because we know the modularity of the theta function. So for those of you, just to set the notation, K has to be equal to R mod 2m, and this is just the usual theta function. And another property which follows from the modular transformation is that this vector value modular form vector value modular form actually contains a little bit of redundant information, because when you reflect it, it's related in this way. So it's plus or minus under reflection depending on the weight. You just go from z to minus z basically and see how it transforms. And from now on, for the purpose of the talk, we will take w to be 1. So then this is negative upon reflection. Okay. There's something I forgot to say, but it's okay. Spill water.
So W is the weight of the Jacobi form, not of the H's.
That's right. The H will have weight W1. W minus a half, sorry.
Yeah.
Yeah.
So do you have to assume that the Jacobi form is homomorphic in Z or something?
Yes. Well, from
That's implied on the.
here, I'm assuming it. Otherwise, you won't have a theta decomposition.
But later you're not going to.
Yes. You see right through me. So then, from this property, you can write phi. You can sort of cut your vector in half and write phi in this way. While this guy is just, right? It just follows from this and this. And then you can ask a question. So what are the matrices of size m minus 1, let's say? M here is the index, such that the following two condition holds. The first condition is that this combination is again a Jacobi form of weight W index same. W equals 1, let's say. Okay, so what do I mean by that notation? I'm just writing this as this. Okay, so I think this notation is clear. We insert this matrix. So this is a modularity constraint, and we also want to impose an integrality and positivity constraint given this natural notation. If you ask this question, and the answer is that such matrices is given 1-to-1 to A, D, E root systems with, for instance, if I'll call, if the corresponding ADE root system is Y, I'll call this matrix NY, and M will be the Cossiter number of this. Okay? This is a theorem, and I have to say that it's all the technical part of the proof is done by Capelli, Zixen, and Zuberg in the 80s. Okay, and their motivation is to look at, to have an AD classification of A1 Kac-Moody theories. Okay, and then we can easily.
Motivation behind the second condition, this integrality and positivity condition. I mean, it's natural from the Capelli, Zixen, Zuberg
Right.
point of view, but in the present context.
Because it works.
But
we want moonshine. We want positive integers that could be dimensions of vector spaces.
So you don't want to have any virtual representations or.
We don't want virtual
Preferably not.
massive levels, and we want integers. Yeah.
But what's the n11 equal to 1 condition?
Well, that one will be completely released later. Actually, N11 will be 24. So.
You can still classify these things if you drop N11.
Mm.
You can still classify if you wanted to.
I see. Well, actually, without this, even without the second condition, you can classify it. You just don't get ADE, but.
I guess you could say we want a single polar term in the H1 component. We don't want to change that condition. So we're fixing the polar term in one component.
So that's the n11 equal to 1 condition?
Yeah.
Actually, we always break this because we always take linear combinations. We never have n11 equals 1 for our nx. We always have n11 equals 24, though. So that's not really. But we can talk about that later, maybe. And now, it's very closely related to your question. We now want to define, if we take a union of such AD thing, then the corresponding matrix will be just the sum of it. Okay, that's a natural definition.
You're not multiplying it by an m. How do you get 24? You don't multiply it by mi or something?
How do I get 24?
Sorry, these are. You don't need to do this.
What? No. How? Okay, for instance, if we take we want to apply it to the Niemeyer thing.
12 copies of A2.
Right, exactly. Then you get nx. 24 copies of NA1, and its 1 component will be.
But what about the 12 copies of A2?
Right, so that would be 12 and so on. I was lying. Yeah, sorry. I'm a big liar. All right. So we've gone through let's say, the most technical part, hopefully the modular stuff. Now we can start to apply it to define this guy and this guy for you. That sound like a plan? All right, so the third part, define this for you and then define this for you. Okay, so this is easy enough. So let y be as in condition this, so it's a union of ADE with the same Cossiter number. Then we can do this. Okay, so I'm going to explain these things. This is, it means that in vector notation, okay, we have this matrix is defined, and this is something I forgot to say earlier, which I was planning to, but this is theta series, which has, again, a canonical form. Okay? So, in other words, this will be a vector value cos form. Take an example. Y equals A1, then it has only one component, and this is up to some prefactor you can work out, eta to the cubed. The familiar shadow for the M24 case. Okay, so now I can define S of x for you. And here comes an interesting theorem. This is close in spirit with to Greg's question yesterday or Ken's comments yesterday. So what is the canonical choice of Mach modular form with a given shadow? And the theorem says that for such y, consider a weight half. Well, it's already this redundant information if you want. Mach modular form, I call it h of y with shadow s of y, which moreover satisfies what we call the optimal pole condition, which says for every element in the vector value Mach modular form, its degree of poles at I infinity cannot exceed 1/4am. Okay? And the theorem says that such a Mach modular form is unique up to multiplication if it exists. Okay? And then you can work out that for any of such so now we only these two theorems are for for y that only that satisfies for any y that satisfies the condition 1.1, namely they are unions of AD diagrams with the same Cossiter number. But you can put, we want to put on a second condition, namely the total rank is 24. And if you do that, then you can prove that such h of x always exists.
Let me understand. You're
Yeah.
trying to make the weakest possible polar term.
Right.
This doesn't allow any polar terms for r other than 1, because they wouldn't be.
Well, yeah, or r squared congruent to 1. Yes.
Making this unique is that you're asking for the weakest possible
Is this condition?
polar
Yeah.
term.
The weakest possible. Yeah.
Alternatively, you can think about the theory of Poincare series as a unique solution.
That's exactly right. That was yeah. That's exactly right. Okay, so I finished all the more painful stuff to give you a feeling of what how these things are constructed, and finally, I would like to put things into context a little bit. If there is no more question for the more technical part.
Let's see, I mean, in Matthias' talk, so there's some question of the uniqueness of the multiplier system.
Uh-huh.
I think you're suggesting.
Well, that is in that direction that I'm not covering.
Ah.
Yes. Here, the multiplier system is fixed by s of x. Yeah. So, context. What does this exercise mean for, the Mach Moonshine? So first, let's see how we get the familiar M24 story from this. So let's take this being 24 copies of A1. So we know the Cossiter number of A1 is 2, and the group is M24. And if you follow this procedure, the Mach modular form you have, then this is Z mod 2, right? So you have two components, 1 and minus 1, but there's a reflection property. Is just nothing but the original function you got And how is that related to Matthias' presentation? We know that from Matthias' presentation, he started with the weight 0, index m-1, so now it's 1, Jacobi form, which happens to be the K3 elliptic genus. So this is 24. And these numbers are the ANs, right? And how do you go from this to this? It sounds like it has nothing to do with each other, these two formulations. Well, the story is like this. There is a very nice and canonical weight 1, index 1 guy, which has a pole at z equals 0. And if you multiply by it the elliptic genus of K3, you get a meromorphic, as Terry anticipated, a meromorphic Jacobi form of weight 1, index 2. Generally, they will be replaced by the Cassiter number. Jacobi form with poles, with a simple pole, again at 0. At 0, of course, what I really mean is at all integral points. Okay. And Zwegers, later Daboker, Murti, and Zamir is here, has told us how to deal with these meromorphic Jacobi forms. They say that there is a canonical way to separate a meromorphic Jacobi form into two parts. This is the polar part, and so as a result, this finite part will be holomorphic. But because of this subtraction, we won't have the Jacobi property anymore, so this will be Mach. To be more precise, now it's holomorphic in Z, as we said, so we can do again a theta expansion as before. And the slogan that Jacobi form contains the same information as vector value modular form will now be replaced by meromorphic Jacobi form has the same information as a given vector value Mach modular form. Okay, and these Mach modular form that you get from elliptic genus in this way is exactly this in this case. Okay, so that's a relation between elliptic genus and our construction. And
little picky.
Yeah.
I think that arrow doesn't go both ways.
No, it doesn't. I mean, generally this,
because
you have to have specific type of shadows.
I'm saying that there could be meromorphic Jacobi forms which give 0.
Yeah.
As a finite part.
Yeah. But yeah. Thank you for the comment. Huh?
The order of the pole must be
1 or 2. Yes. Sure. I'm not trying to make a sweeping theorem here. It's a slogan. Okay, so the natural question is, we like ZK3 because it has a clear physical meaning. What about all the other HX that we have constructed? Okay, so in particular, we can do this exercise for all the Niemeyer lattices. How about the counterpart of ZK3? So case 1 will be the pure A type that I wrote down here. It's the yellow that's labeled by divisors of 24. That would be M24 divided by K copies of this. And again, we can have a map from h of x to this meromorphic guy. And then by dividing it with this guy, you have a nice weak Jacobi form. So again, it then leads to n equals 4 character decomposition, but which has no clear CFT interpretation. Probably not. And the case 2, which are the other ones, okay? Then this guy, you can do this, assemble it into meromorphic guy, no problem. But this has poles at torsion points.
Not case 1, is it?
Not case 1. Yeah, there are only 2 cases. So then you cannot pull this trig. So the arrow stops there. You cannot even ask for n equals 4 characters and so on. So there are two possible attitudes you can take. The first one is to say, okay, so I like M24 because it has this relation, nice relation to geometry and physics. So we should stick to that case. And the second attitude would be, so if this is the case, then maybe ZK3 is not the right thing to look at. Whatever that's interesting physics or mathematics that's going to explain this mystery should accommodate this Mach structure and the Niemeyer structure. So the jury is out which two, or maybe none of them, is correct. And I have some more things to say.
Can I ask one question? What's the sample charge of the n equals 4? Is it always 6?
No, it's 6 times mx minus 1. Okay.
Who cares if we lose n equals 4? What good is n equals 4 anyways?
That's what I think.
So it's not an elliptic genus of some hyperscalar manifold of that dimension?
No.
How do you know that?
You know that because it doesn't have a character in the Riemann sector that under spectral flow would be the identity in the Schwartz sector. So it's a conformal field theory. If it's elliptic genus of a conformal field theory, it's a conformal field theory that doesn't have the identity operator in the Schwartz sector.
What about a non-compact manifold?
That's a very interesting idea.
Yeah.
I'm not sure. I have a question and a couple comments.
Uh-huh.
The first comment is when I was saying earlier that you do have genus 0, that's actually another way of seeing that when you restricted those polar conditions, you knew you were going to get integer coefficients for your SY.
Really?
Absolutely.
You had to teach me that.
Those polar conditions, once you have a cusp form of weight 2,
Uh-huh.
the preimage of these weight 3 halves things will start having transcendental coefficients.
Right.
So the second theorem I produced yesterday was really about that picture when we had positive genus.
Uh-huh.
Right, so now here I want to get to the point. If you remember, my theorem was that the coefficients of the holomorphic part of the harmonic Moss forms I produced were numbers which grow exponentially, just like your numbers.
Right.
They tend to be transcendental.
Yes.
But the obstruction to being algebraic I showed was the derivative. If you subtract off the derivative, you take a norm, you get a gigantic integer. Speculation: is there a moonshine or something resembling a generalization for moonshine, where all of the coefficients of the lifts of your canonical forms of these minimal parts are degrees of something algebraic plus a perturbation which comes from the derivatives or like existence of rational points in modular elliptic curves? Because the theorem I proved is your picture without worrying about an L cross. But generically, those coefficients are transcendental, which I proved for you. That's where you get rank 0 versus rank 1 curves. But there is a large integer there.
I see.
And in the case of integers, you have all of these polynomials which we can prove are irreducible,
right.
generate Hilbert class fields. So I think going upstairs, generically when the genus is positive,
Right.
going downstairs when you have integral coefficients, there's very, very beautiful mathematics. I don't know if people in physics really care, but to number theorists, I think we would care.
Yeah. So yeah, actually, that if I may still make a comment, I mean that might, there's a theorem here.
There's lots of theorems here.
Which says that I say that y of x, y of x, what am I saying? Which says this is unique if it exists.
Yeah, sure.
And here we say that
It's transcendental.
here we say that let's restrict to pure A. Okay? Then this exists if and only if K is divisor of 24. So the Niemeyer is singled out. You can't do better than Niemeyer if you want to do pure A.
Replace what you call for L. What is the geometric object that's giving the gigantic integer parts?
Right.
I mean, m goes to, there's a theta function for every m. There's a vector for every m. It's easy to write down. What geometrically is that corresponding to in Moonshine? It's not going to be spot on the nose because there's going to be occasionally.
I'm saying that if I am allowed to restrict to my optimal pole condition, then it's very sparse. This is extremely sparse.
But I'm speculating that there is a natural sequence of integers for every m. M is 132. That doesn't fit your picture. But I can produce for you a canonical sequence of integers that behave like your A of n.
But not the integers of x.
I know that.
Yeah.
I know, that's what I'm
Okay.
saying. And
Yeah.
I'm asking.
They won't all be
What is it?
positive, though, right?
I have to think about that. Actually, I think they will be positive for the same reasons coming from. If they aren't, they'll be certainly periodic. They'll be periodic with multiple. The signs will be periodic with respect to m, but in absolute value, they'll certainly go to infinity.
Because all these examples have the property that all the analog of the AMs, except for the polar guy, are all positive
Right.
integers.
Right.
Which.
Right. I'm allowed to take absolute values.
Yeah, the positivity is much. For instance, in the paper by Zamir and
Sequence of integers.
and
Yeah,
Don
there.
and Don, there are examples which satisfies the optimal condition but have non-integer, non-positive coefficients, integral coefficients. But if I may just finish up, I just say that again. So I hope I convince you that there's a uniform construction and of these moonshines, and well, one might just focus on M24, or one might try to incorporate them in some way altogether, and that's that's the end.
There's been lots of questions, and we should, unless we should.
Why not allow questions? Because it seems like there have been very few questions allowed after seminars, and often the questions are an interesting part.
Yeah,
So
I'm happy with
do we?
that.
I mean, is the 5 minutes, 10 minutes for lunch so urgent, or can we allow questions?
Sure, absolutely. Let's go for it. So,
Okay, so here you're sort of giving up n is equal to 4, so to complement integer.
Yeah, of course.
Are you replacing it by something else?
Not that I know of, but it must
No,
be something
so-
else. There must be something else that's more fundamental, but I don't know what it is right now.
It seems like you're also losing subsymmetry.
Yeah, I'm losing any kind of
And
contact to physics at this point.
I didn't catch Toru's question, but I think it might be related to mine. Which is, you know very well that, I think I'm just repeating what Toru just said. As you know very well, these meromorphic Jacobi forms and this vector valued modular forms show up in black hole counting functions for 4-dimensional n equals 2.
Yeah, 4-dimensional
So, I mean,
equals
the
2. So you're not referring
4-dimensional n
to.
equals 2, for example, type 2 on Galois, wrapping the d branes.
Yes.
Okay. So, do the examples that you're looking at, these h-axes, do they correspond to any particular black hole?
Well, I think Samir might have more to say to that, but my impression is the examples they got has
N
double
equal to
poles.
4 is, had double poles. They were
Yeah.
not, these things didn't.
Our examples
we-
have single.
we don't know.
So the answer
Single
is
poles.
you don't know, or that the answer is no.
No, the answer is that in n equal to 4, it doesn't. The answer is no. But in n equal,
I'm talking about n equals 2.
yeah, so I don't
Then
know. There the answer is
I don't know. I haven't seen that.
And
But that would be an interesting place to start, for instance. With that.
I mean, the n equals 2, they tend to have very deep polar terms, right?
Yeah, yeah. If you want, this
If you
is
have
like very tiny central charge or whatever.
Right.
That's yeah, very quantum black holes. If you want.
actually, that's true also for the n equal to 4 examples. It's the ones with the lowest polar terms have, as far as I can see, nothing to do with black holes directly.
Yes.
You can calculate the coefficients of ordinary modular functions by using algebraic relations between them.
Yeah.
Is there a similar technique for calculating the coefficients of modular forms?
I think so. By relating them to modular forms, right? Is that?
But don't look at me. Look at it after these guys leave.
I mean some generalization of the argument principle where the first n coefficients plus the divisor determines the n plus first one? Sure, absolutely.
Well, you can use homomorphic projection.
Yeah, absolutely. Can I ask a very naive question?
No.
Would it be
other people
surprising?
ask.
Don't. I'm sorry, Jeff.
No. I like your questions, but
Okay,
David.
Dave first.
Well, mine is a sort of very light question. Why umbral?
Oh yeah, because the word shadow, right? Umbra is the Latin for shadow.
Shadow.
We were thinking about moonlight shadow, but that might be a little bit too hippie. So.
probably a trivial question. So in case 2, in the case where the root lattice is 3e8,
Yeah.
it's equal to the whole thing.
Yeah.
Sometimes that's sort of exceptional in this sort of business. Is there anything particularly interesting about that case or trivial?
Yeah, we have 4 copies of E6. We have 3 copies of E8.
Yeah, but E8's holomorphic. I mean, it's the whole Niemeyer lattice already.
From that point of view, no, there's not. I mean, they're exceptional, but nothing. But you should think about it.
So can you take a cube root of it, for example? Can you in some sense take a cube root of that example?
No, the coefficient starts with 2.
Okay.
If it starts with 1, then I feel better.
So here's my question.
Yeah.
Going back to the very original help modules that appeared in Moonshine, would
Yes.
it be interesting to find a map just using these character degrees that produced in order all the coefficients of some of those help modules?
Which map? If I take the
If I told you I could define a map that took
Right.
those character degrees, like those A of n's, the 24, the
Okay,
90,
yes.
and produce the Q expansion of J, or a character for one of these other groups, would that be interesting? Powers of that, because we can do that. That exists.
What's
What would the physical meaning of that be?
what is the relation between these functions and J functions?
Well, this is what I was saying earlier when there's a whole family of modular functions on
So
a
you say
modular
that
curve of genus
there's
0
a
living below
recursive
it.
relation relating all of them?
It comes from classical algebraic number theory.
Well,
If
there-
delta is a discriminant for class number 1, for free you're going to get a help module plus a constant.
I mean, you might be associating this theory as 1 for each conjugacy class in the monster. That's more
Well,
or
I
less
want-
what he's saying, or sort of.
Not quite.
I'm making
not
up something
quite.
that you could prove
No,
from a
but
modular form perspective. Does
Right.
it have a physical meaning?
Well, I think it's an interesting question to ask from a representation point of view. Like, what does it mean for a
Because
representation?
we do
they
have relationships
all
between all these various
extend-
kinds of
right,
groups.
Right. Do they all extend from monster in some ways? I mean, that's under control. I mean, because all these groups, as you can see, are subgroups of Conway, right? All these G of X. Because that's implicit in the deep hole picture I gave you. Because then, you know, you have.
They're
I think you
mesfield
can do
groups
that.
usually.
Yeah.
I mean, apart from the first 6 or so, they're really small.
Yeah. They are, for instance, for instance, for this guy, The group is identity. Not very cool.
Okay, any other questions? I'm sure there are many other questions. By the way, if there are any questions, if for example, you have a lot of complaints about the way the conference has been organized, I would strongly suggest that you that she's done almost all the work. She's the one to. Okay, thank you again for.